I will present on behalf of the Lima-2 CSCS mission team the recent results from the Seismo Electromagnetic Satellite CSCS mission. The current status of the mission is that it has been launched on February 2nd, 2018 at an altitude of 507 kilometers in the upper ionosphere on a polar orbit. The state of the satellite platform, that is the position of the platform, is very stable, is running over the seismic belt, covering that continuously. The working mode operates perfectly, meeting the ground design, and the data are very clean, and the electrical situation of the satellite is fully under control. The CSCS satellite is a state-of-the-art in measuring all the different physical quantities which can be observed in the magnetosphere. And is equipped with the state-of-the-art scientific payload, starting with a high-precision magnetometer from DC to 16 Hertz, based on 2 flux gates coupled in a dark state magnetometer. The search coil magnetometer, SCM, which is operating between 10 Hertz and 20 kilohertz. The electric field detector, EFD, operating between DC to 3.5 megahertz. The plasma analyzer package, PAP, measuring the ion density between 100 and 10 to the 7 per centimeter cube, ion temperature between 500 and 10,000 K, ion content, charge hydrogen, charge helium, charge oxygen, and ion drift velocity. A Langmuir probe measuring the electron density between 10 to the 2, 10 to the 7 per centimeter cube, electron temperature between 500 and 10,000 K, and the GNSS occultation receiver measuring the TEC and the profile of neon, the air refraction index, and the profile of the air temperature and pressure, as well as ionospheric scintillation index. Then we have a 2 detector to measure charged particle at higher energy, the HHPP, measuring proton fluxes between 1.5 MeV to 200 MeV, electron fluxes between above 100 keV with a pitch angle resolution of 5 degrees, and the energetic particle detector built in Italy, called also Lima-2, and is a high energy particle detector, measuring proton flux from 30 to 100 MeV and electron flux between 30 and 200 MeV. This is one of the tests being performed on the Italian high energy particle detector in Frascati in the top figure, and in Trento in the bottom photograph, scanning electron and proton energies between 30, 45, 60, 90, 120 MeV for electron, and up to 202 MeV from 37 MeV for protons. Several acquisitions with the cosmic units has also been performed before delivering the detector to China. In flight, with the possibility to compare and cross-calibrate the 2 detectors, having in this way an instrument which can cover an energy range between some MeV to 100, a few hundred MeV, with a very good angular resolution and a wide acceptance from the area point of view. And those are some results showing that we can see very clearly the fluxes at different latitude. In particular, very visible the South Atlantic anomaly, as well as a part of the radiation belt at higher latitude observed with the 2 detectors. Being the HEPD capable to measure a high energy electrical charged particle, we can also measure fluxes of galactic cosmic rays, which can be compared with the models taking into account the geomagnetic cutoff, and this has been done and checked thoroughly. Charged particles are also very sensitive to space weather condition, and these are some results from the HPD showing the variation on particle fluxes at high energy in conjunction with the August 2018 geomagnetic storm, a class G3 storm, which has occurred. This is an example of the sensitivity of these particle fluxes to disturbances coming from the outside. But the CSCS has been conceived to allow the precise measurement of many physical observables involving the lithosphere, atmosphere, ionosphere, magnetosphere coupling. And in addition to those variables, if we use variables which can be extracted from other satellite or ground data, we can achieve a global picture of the phenomena associated to seismic activity, use space as a privileged point of view, opening for the possibility of a different way of observing Earth based on those non-optical variables. Indeed, particle trapped in the Van Allen belt has been shown to be sensitive to phenomena happening on ground. So the magnetosphere where they are trapped is coupled to ground in some ways. And this has been published some time ago, where we saw the correlation with the co-seismic correlation between 300 keV electron using the NOAA-POISE satellite and large seismic event above a Richter scale of 5. These earthquake and wave particle interaction times were compatible with the delta t equal to 0 after correction for the drift time, and with the accuracy of the observation of about 15 minutes. And so we see that there is an interaction which travels to the magnetosphere. The question is how this interaction is traversing the atmosphere, the magnetosphere. And the idea is that at the beginning, the first interaction takes place between the Earth and the atmosphere, creating an acoustic gravity wave, which is then traveling to the ionosphere and then coupling to the magnetosphere. The CSS-APD data have been collected at different values of energy and pitch angle and L value, and those fluxes, which are basically fluxes connected to the Van Allen belt, are being used as a reference for searching particle burst. So in order to understand this interaction, we develop a model called MILC, MILC model, which is magnetosphere, which stands for magnetosphere, ionosphere, lithosphere coupling model. And it is based on the coupling between the Earth surface, can be liquid, can be solid, and acoustic gravity wave propagating to the atmosphere, creating in the ionized plasma emission of electromagnetic waves which travel to the magnetosphere. And in the magnetosphere have two effects. They change the frequency of the line resonance frequency of the magnetic field coupled to the plasma, as well disturbing the Van Allen belt particle, making them moving and precipitating to different L values. And among other variables, the TC content can be also studied with GPS and its variation, as has been shown in previous example. So we take an example of the Bayan earthquake to make this comprehensive analysis on earthquake, which is following the interaction which I mentioned before. So the Bayan earthquake was a 6.8 earthquake taking place on August 5, 2018 at UT 1146. CSCS was orbiting in the vicinity, but not above the earthquake at about that time. So the question is, can we see the various phenomena which we introduced in the previous slides? The earthquake took place in latitude minus 8.3 in the Sumatra region. We start with AGW observation using ERA-5 satellite data and studying its temperature profile using the literature for this kind of phenomenon, and evaluating the presence of an acoustic gravity wave. Indeed, after taking the temperature variation with respect to the standard reference, we clearly see the presence of acoustic gravity wave in evolution above the earthquake on the time corresponding to the earthquake. This can be also shown in those three plots, data taken on August 3rd, August 4th, and on the day of the earthquake in the vicinity of 12 UT the time of the earthquake. We clearly see that the condition of the meteorology condition are very stable. In the previous 2 days, there is no presence of acoustic gravity wave, while on the time of the earthquake on August 5, there is clear evidence for this phenomenon. The analysis of ionospheric TEC also indicate some anomaly with respect to the average taken on August 2018 at that location. We see 2 anomalies. The first anomaly, we start at 5:45 UT, and the second anomaly, we start at 9 UT, and then peaking at 11:45 when there is this earthquake. So this is potentially in relation with the earthquake. More indication of a connection can be observed with studying the frequency variation of the line resonance frequency. We made the analysis using ground-based stations, and we observed that there are 2 steps in the frequency. The standard frequency for this particular line is just above 80 millihertz, 75 millihertz. We see a first modification at about 540 UT, a decrease between 100 millihertz to 80 millihertz, and the second jump at about at the time of the earthquake, 11:45, which goes from 75 millihertz to 64 millihertz. So this second phenomenon is clearly correlated with the earthquake, and the first jump is happening before the earthquake, basically at the same time when we observe the TEC variations. The CSES observation were done also using the electric field, the magnetic field, and the LAGMI probe observables. And we observed that on August 11:31, we took the average condition as a background. We noticed that in the vicinity of the earthquake, we had anomalous peaks at 180 Hertz on the Y and Z electric field component, and at 630 Hertz in the EY component. And if we do the same observation for the magnetic search coil, we observe that there is anomalous peak at the same frequency at 180 Hertz as for the electric observation, but this time is the BX and the BZ component. So the 2 components of the electric and the magnetic field happen to be on orthogonal planes. So we are observing an electromagnetic wave at very low frequency, 180 Hertz. If we study the Poynting flux correlated to these electromagnetic waves, we observe a clear presence of a Poynting flux, which is corresponding to electromagnetic wave coming downward. We then observe a LAGMI probe observation also on August 5, and we see clear presence of 2 anomalies density component, one happening at 5:45 and the second connected to the earthquake. There is a clear plasma density wave detected over the location of the earthquake. All those data then support the evidence of a clear correlation between coupling between the lithosphere and the ionosphere and the magnetosphere, described by the model which we introduced, the MILC. And our future work will be related to extend this study for correlation to other earthquake in order to complete this study of the model, adapting to systematic observation of different type of earthquake in different locations of the Earth. I thank you for your attention.